human bodies. So the most famous projects are visible human project. They are conducted in USA, China, and Korea. In this project, a database of images of the whole real human body was built by cutting a cadaver, the dead body, using milling machines. So this is the real body. So this is the milling machine. So they cut a cadaver at 1 millimeter intervals, and they took a picture of the cutting surface, and they made a database of the cutting sections. So this is the result. So if you want to study the Bio-CAD modeling, you can freely use this kind of database. So in Korea, the KIST, the adjacent of this KIST, inside maybe KIST is located in KIST. So you can obtain the database from KIST. So I also used the database obtained by KIST. So after obtaining the CT images of human bodies, we can reconstruct 3D shape using the CT images. There are many reconstruction methods. So the first method is known as control skinning method. In this method, firstly, we must divide the region of interest into separate images, because in CT images there are many organs. In this image, this is muscle, and this is bone, and there are also arteries. So if because I wanted to make a shape of a bone, so I needed to separate the bone images from others. So this is the separated bone images, and then the boundary points for each images are extracted and interpolated into a contour curve like this. And then finally, a skinning surface can be generated through the whole contour curves. However, it is very difficult to construct such a surface automatically, because the skinning operation is very hard to operate and treat. Additionally, the result, because when we interpolate these contour curves, some kind of aliasing or overfitting can be occurred. Another methods are volume polygonization methods. In this method, the CT images are converted into polygon meshes. They are most popular method to reconstruct human bodies from CT images. But as you can see in this image, the result is the unsmoothed surface, and as you can see, so there are also aliasing. There exists aliasing. Alias means the shape. Alias means the phenomena that the shape looks like stairs. There are among volume polygonization method, the most well-known method is the matching cube method. Here is the basic algorithm of the matching cube method. In the matching cube method, the matching cube method, is algorithm to convert an isosurface of a scalar field into triangular masses. Because the CT images is a kind of scalar field, because the CT images are represented by pixel values. So it is a kind of scalar field. So in this figure, in this CT image, the background has the 0 value, and the bone has the 255 value. So we can represent the boundary as 128 value pixels. So if we extract the iso curve or iso surface having 128 values, we can extract the boundary curve or boundary surfaces. So in matching cube method, this is the grid representation of this CT image. So the background color, the background is represented by a blue point, and the white color means the 2055 pixel value is represented as a red point in this grid. So if we want to extract the value of 128, we can interpolate because the blue point is 0 and the red point is 255. So you can imagine that the 128 point can be located within these 2 points. So for each square, we can find this such a point, and then we can connect all the points represented as a purple color. So if we connect all these points using lines, we can obtain the boundary curve. So if we extend this algorithm into 3-dimensional, we can also obtain a boundary surface. This is the matching cube method. So it is usually used to reconstruct 3D shape from CT images. Another methods are implicit function interpolation method. In this figure, if this figure is a CT image, and if we want to extract the boundary, we can assign 0 value into the boundary point, and then we can assign the negative value into the inside of a bone, and then we can also assign positive value into the background point. And then after that, if we interpolate some kind of implicit function using this point, we can make implicit function representing the whole CT image. And then from the implicit function, if we extract the zero value point, we can make some kind of the boundary curve. In implicit function interpolation method, the most popular function used to interpolate is the radial basis function. So when you use radial basis function, the smooth surface can be obtained. So this is the example of implicit function interpolation. So the points are the pixel in CT images, and if we use this method, we can obtain a smooth surface. But the most big problem when you the big problem of this method is it needs a large amount of computer memories, and additionally the commercial CAD system cannot support implicit function representation. So when we want to use the result inside commercial CAD system, we need to convert the implicit function into polygon. If you want to convert implicit function into polygon, you can also use the matching cube method, because implicit function representation is some kind of scalar field. So in my method, they are the previous works. So from now on, I would like to my research result. So I started with CT images of human, and firstly I segmented. I divided this CT image into bone part and other part, and then I extracted bone part only. So this procedure is called image segmentation. And then using this segmented image, I reconstructed 3D shape. As I said just before, because CT CT cannot distinguish the target organ or bone from other organs. Firstly, we need to extract the region of interest. So in CT images, firstly I extracted the bone images. So such a procedural process is called image segmentation. Usually, image segmentation is performed manually because it is very hard to know which part is bone or which part is muscles, because the resolution is very low, and even doctors cannot exactly distinguish a bone and muscles. So it is very hard to automatically segment an image. So in my method, I performed image segmentation semi-automatically. For example, firstly, I extracted the bone part using threshold filter. In CT image, the organs has their own pixel values. For example, the air part has negative 1000 value, and the water has 0 value, and bone part has a value rather than 100 or 200 values. So in this image, I extracted the pixels having the value larger than 100. So then we can obtain this kind of image. But the values of pixels are from 100 to 1000, 2000. So I converted the background into 0 value and other parts into 255. So this image has only 2 values. So it is called binarization. And then using finding connected component filters, I clustered the pixels into several parts. So if we connect pixels, if we try to find the connected pixels, and then this image can be divided into 4 parts because they are connected each other. So we can make this one part, and this part is also connected each other. This part is also connected each other. So we can cluster images into 4 parts. And then user want to reconstruct this part, and then you can extract this part into another images. In this procedure, user should manually select the one part. And then if this image is inverted, then we can obtain this kind of result. And then in this image, we can also find the connected component. And here, we find the maximum connected component. So the background is actually maximum connected component. So we can select the background color. So in this image, the white. And then we revert again the image. We can obtain this bone part. So the image segment in this using through this process, we can obtain the bone part only. But there are several sharp or small pixels. So to make the smoothed images, I use the morphological filter, and then we can obtain some smoothed image of a bone. And then using these segmented images, I reconstructed 3D shapes. This shows the whole procedure for the shape reconstruction. There are many stages. Firstly, I made the image smooth using Gaussian filter. So this is the segmented image just to be obtained in the previous page. And then I made this image into this kind of smooth image. Because to reconstruct the 3D shape, I used the matching cube method. But when I applied the matching cube method to this image, the result was shown like this. As you can see, there are many stair-like shapes. So, but after Gaussian filter was applied, then we can obtain more smoothed shapes. So, I used the Gaussian filter before applying a matching cube method. And then, as I said, I applied the matching cube method into these images. So this is the result from the matching cube method. But there are still exist stair-like shapes. As you can see, this shape has a lot of triangles. There are many triangles, about 162,000, 2,000, blah blah blah. And then there also exist the stair-like shapes. So to make the shape smoother and to reduce the number of triangles, I use the triangle decimation technique. I will show you some movie clips. This is the sorry. This is the technique called triangle decimation. this one has many triangles, but we can reduce the triangle dynamically. So we can adjust the level of details using triangle decimation technique. So I applied this technique into my 3D shape, reconstructed from the CT images. So after applying the triangle deformation, I obtained this kind of result. This shape has a tenth of the original triangles. This image has 1.5% triangles of the original triangles. And then I also interpolated these triangles using triangular measure patches. The basic principle is to interpolate each triangle into triangular measure patches. Triangular measure patch is one kind of representation of triangular surface. So, using triangular measure patches, we can convert each triangle into the curved triangular patches. And this is the final result of the first stage. And this is the right femur, this part, and this hip bones. This is the artery. So the total time to reconstruct this kind of shape from the original CT images was about within 10 minutes. It is very short time. This result only represents the outer boundary of a bone. But in my research, I also want to represent the inside of a bone into a function. There are many researches to represent heterogeneous model or heterogeneous objects. The most simple method is a descriptive model. So in this model, the total volume is divided into uniform elements like this. And each element is represented by a specific material property value. So in this representation, the accuracy depends on the resolution. The higher the accuracy is, the more storage space is also required. The function-based model. In the function-based model, the material distribution is represented by an explicit function. So, however, to make such a function is very difficult. So, in the previous research, they proposed the control feature-based model. In this model, user just to provide some kind of control section. For example, in this video, we make a function, simple function like this, and we can assign the material property into here, and we can also make a circular function and we can assign specific value to this function, and then after we interpolate using these two functions, we can make this kind of function. This is the function-based model. But when using this method, it is very difficult to represent complex or irregular shape, because to represent irregular shape representing irregular shape using a function is very difficult. So most popular method to represent heterogeneous model is control point based model. In this method, the heterogeneous object is represented by B-spline function. So, when we use B-spline function is defined by several control points. So if we control the control points, we can adjust the total or the whole shape easily. So it is suitable for representing the heterogeneity of a bone. So I use the control point based model. So in my study, I used the control-based model to represent the heterogeneity of a bone. So the pixels in CT images are interpolated with B-spline volume functions. B-spline volume function is an extension of a B-spline surface into 3 dimensions. So actually, B-spline function is mostly used for CAD system to represent freeform surface. In my research, I extended in 3 dimensions. So it is called B-spline volume function. B-spline volume functions are defined like this. But I'm not going to explain the B-spline volume function in detail. So it is very complex functions. So most important portion is the P. It is the control point of the B-spline volume function. And in geometric modeling or CAD, the P, the control points are usually used to represent the location of the geometry. But in this research, I also assign the material property into the last element. The last element in the control point in my research means the house field unit. Actually, the pixel value in CT image use the unit of household field, shortly H value. It is different from the image pixel value. RGB, it is not RGB or grayscale value. HU value is closely related to the density value, density. So as I mentioned, the air has negative 1000, the water has 0, and bone has a value larger than 100, 100. And in my research, B-spline volume functions, which is defined like this, are defined by interpolating the HU values in CT images. the formulation of the interpolation is like this, but I'm not going to explain about them in detail. After the interpolation, we can obtain the B-spline volume function representing the H values of CT image. These are results. Actually, the original CT image has discrete value because they consist of pixels. But after interpolating using B-spline volume functions, the result is a continuous function. And then this, I converted the grayscale value into color images. So we can see the density variation. Yeah. In the second stage, in the first stage, I reconstructed the 3D shape of a bone, and I made a function representing the property value of the inside of a bone. In the second stage, I studied the finite element modeling of the heterogeneous bone using the reconstructed shape and the B-spline volume function. There were many studies, but all of them represented the finite element as a homogeneous or composite element. This is the homogeneous element, and this is the composite element. The feature of these elements is that one element has only one material property. In my study, I represented the finite element using the graded finite elements. The graded finite element can have the material property varies from point to point. So I made the finite elements models of a bone using the graded finite elements. So for finite element modeling, firstly, tetrahedral elements are generated from the constructed bone shape. I used to make mesh from the constructed shape. I used the mesh module of the ACES. It is a commercial library. For the finite element analysis, the material properties should be assigned to each element or each node. So we need to find some kind of density or elastic modulus or force ratio to analyze the finite element model. So, however, the B-spline volume function that I formulated has only HU values of CT images. However, the HU values are closely related to the density. So some researchers studied how to convert the HU value into density. So we can convert the HU value into density using this formula. And there are also another formula to convert density into elastic modulus or force ratio. So using this formula, I could derive the material properties from HU value. in this figure, this figure shows the density distribution derived from the H values. So I assign the density and the Lessing modulus and Poisson ratios into each node of the elements. And I also derived the mathematical model for the finite graded element. This shows the formulas to derive the finite element model, but I will skip this. Additionally, I developed the finite graded element solver, because the commercial solver cannot support the finite graded element. So I implemented the solver for myself using C++ languages, and this is the analysis result. This shows the stress distribution, and this shows the displacement. In the last stage, I studied how to print the heterogeneous form using 3D printers. The goal of the last stage is to fabricate the heterogeneous bone using 3D printers. Especially, I wanted to represent the porous structure of a bone, because this shows the microstructure of a real bone. Bone has many holes inside the bone. It is a porous structure. So, in the previous study, a porous structure was represented just as regular patterns. So in my study, I wanted to represent such a structure as similar as possible. Actually, I did two things. Firstly, I printed the reconstructed bone shell with material properties. I assigned the material property as a color to each node, and then converted it into a mesh file. And then the mesh file can be printed using 3D printers. So I printed this file using color 3D printer, and this is a printed result. So using this physical model, we can understand well the material distribution or the density distribution. This is another result. As you can see, there are many holes. Actually, as I said, I wanted to represent the porous structure, but the result is not similar to the porous structure. But to represent such porous structure, I used the density distribution functions as a probability function. So in the reconstructed shape, I removed the elements using the probability distribution function. So I randomly eliminated elements with probability of density. So if the density is high, then the element may not be eliminated. But if the density has low values, the elements can be easily eliminated. This is the final page. So, in summary, I started with city images, and firstly I reconstructed the bone shape from city images, and I also formulated the material distribution using display volume functions, and then to analyze further biomechanical analysis, I made the finite element model using the graded finite elements, and then I also developed the graded finite element solvers, because the commercial solvers does not support the graded finite elements. And additionally, I tried to fabricate the heterogeneous bone. So I used the 3D printers. So in this figure, the material distribution is represented as colors. And I also tried to represent the porous structure as similar as possible. So this is the final result. Thank you for your attention, and I apologize my bad English. Thank you. Do you have any question? Yes.
Sir, with respect to 3D printing, it is based on layer by layer.
If we have the polygonal mesh files, the 3D printer automatically analyze the file and they slice the file. So the slicing is the function of 3D printers, so I did not consider slicing. I just provide the mesh file to the 3D printer.
My question is that does 3D printer would create a smooth bone or layer like scale?
I don't know. This is the real result. As you can see, the outcome has very smooth surface. I think the resolution of 3D printer was very good.
Thank you for your seminar.
Thank you.
For your presentation on the basis. So, is it possible to separate the outer surface and the inner surface in a way that we can have the outer surface through different scanning method? Like,
you mean in CT images?
yeah, in parallel to CT images, like we can have direct extraction of the outer surface.
Yeah, outer surface.
You want
also extract. I can. It is possible. Okay. So, however, if we have images, for example, if there is the pole represented by the background color, then the matching cube method can extract the outer surface and the inside surface. No problem.
You apply the FEM on the one which is not porous. So you have a plan to use the porous in the FEM.
Actually, the finite element method assumes that material is has continuous properties, continuous functions. So I think it's very difficult to represent the microstructure. So there are studies to represent a bone using microstructure, but the microstructure has the micrometers unit. So if we represent its shape using micrometers, and it has very tons of elements. So I think it is a resource problem. It's possible. So the research trend is the multi-scale modeling. So the finite element researchers tried to make a model using the multi-scales, microscales and millimeter scales.
And something like the mesh, we make mesh 2 times, like we make a mesh in the yes, and we need a mesh in the FNMF, right?
I can't remember. This is a surface.
Yes.
Yeah, and this is the finite element meshes.
Volume of the volume?
Yeah, right.
Yeah.
The tetrahedral element.
So they are different. We need them.
Yeah, this is a triangle, and this is the tetrahedral. Solid mesh.
Thank you.
So you mentioned to create the porous structure, you use the probability function for the density. What is your what is the probability function based on?
Actually, real bone looks like this. So this part has very low density in real bone. So we in this image, the black part means the white means the very high density, and black part means very low density. So using these values, I use these values as a probability function. So for example, if I decide if this part should be exist or not using the density value. So is an answer? Question? No more? How about you? This question?
Professor, can I ask a personal question?
Yes.
Like, what was your research topic when you were at CAE? Was it
data exchange?
And then you went to Samsung Heavy?
Yeah, Samsung Heavy Industries.
And now you're doing bio-related, right?
This is the finished project. So nowadays I studied machine learning technique for image, drawing images or design.
You have been to Samsung almost 3 years.
Yeah, 3 years.
I remember it's more than 3 years. All right. Thank you.
Thank you.